The mass production of complex industrial components begins with the sudden application of extreme force and heat to raw materials. This is the domain of manufacturing engineering, the systematic study of converting raw materials into precise products by applying specific physical and chemical laws. This discipline replaces manual control with prepared programs and instructions that provide the exact energy and data required for machine-driven production. To manage these sequences, we use process engineering. This field solves developmental problems by identifying the specific parameters that increase production efficiency and maintain dimensional accuracy. Every operation follows this transformation pipeline, beginning with a raw material node, passing through process engineering, and resulting in a final product. The central step is never arbitrary. Our engineering methods are a direct consequence of the raw material's starting variables. During these operations, a material undergoes physical or chemical changes that allow it to become a functional part of a larger assembly. Therefore, to design any production sequence, an engineer must first identify where a material sits within the technical taxonomy to understand its physical constraints. This chart details the formal classification of engineering materials. The first major division separates substances into metallic and non-metallic categories. Metals are polycrystalline bodies consisting of fine crystals. We melt or sinter them with other elements to create alloys with specific structural properties. On the factory floor, metals are categorized by their iron content. They are either ferrous or non-ferrous. Ferrous metals are primarily composed of iron. Because of this chemical makeup, these materials possess magnetic properties. This category includes plain carbon steels, alloy steels, and various types of cast iron, such as gray or malleable iron. Plain carbon steels are further classified by their carbon percentage. Low carbon or mild steel contains less than 0.30% carbon and is used for everything from flat sheets to structural beams. We adjust the material's properties by altering the chemical recipe. Adding aluminum creates drawing quality steel for stretching, while increasing manganese improves the strength of structural steel. Non-ferrous metals, shown on the right side of this taxonomy, contain absolutely no iron. These metals, including aluminum, copper, and zinc, are not attracted to magnets and do not rust in the same way ferrous metals do when exposed to moisture. A material's exact position on this taxonomy defines the mechanical limits of how it can be shaped and utilized. These classifications translate into measurable mechanical behaviors when a material is subjected to industrial loads. Tensile strength is the measure of a material's ability to withstand a pulling force before it fails. This property is expressed as a ratio, the maximum tensile load the material can bear, divided by its original cross-sectional area. Designing for tensile strength is a requirement for machinery parts, jigs, and fixtures, where pulling forces often cause catastrophic tool failure. We also calculate shear strength. This is the maximum load a material withstands before a sliding failure occurs along a specific cross-section. This force is applied during punching operations, where a press tool drives a die through a workpiece to shear out a specific shape. Engineers must also account for elasticity, the property that allows a material to recover its original size and shape after a deforming force is removed. These mechanical properties dictate tooling choices. To shape a workpiece effectively, the material properties of the cutting tool must be significantly superior to the material being cut. High-speed steel, or HSS, is an effective choice for low to medium-strength materials and softer alloys. For harder workpieces, like cast iron or superalloys, we must use cemented carbides or ceramics made from alumina or silicon nitride. Ceramics are chemically inert and extremely heat-resistant, making them ideal for high-speed cutting, though they are limited by their high fragility. Ultimately, the forces required to overcome a material's specific tensile or shear strength dictate the machinery and tooling used to shape it. Once the material properties are defined, engineers select one of three primary physical methods to achieve the final part geometry. The first is subtractive manufacturing. In this process, we attain the required shape by the systematic removal of raw material. This subtractive method involves using high-speed cutters to aggressively shear metal away from a solid block with microscopic precision. This process uses computer numerical control, or CNC, where prepared programs and instructions manage the machine tools instead of manual control. The second category is formative manufacturing. Here, the shape is attained by forcing material to flow or deform into a mold without removing any mass. Casting is a primary formative process. We pour liquid material into a hollow cavity mold and allow it to solidify into the desired shape. We also use compressive stress in forging, where a machine slams a die into a glowing metal billet, compressing it into a specific part. Hot forging is carried out at temperatures above the material's recrystallization point, the temperature where the metal's internal structure can be reshaped without becoming brittle. Forging is often selected over machining because it produces parts with higher ultimate strength and creates significant material savings. The final method is additive manufacturing, where we attain the required shape through the controlled layer-by-layer accumulation of raw material. Whether we cut, crush, or build a material is a direct consequence of that material's position in the engineering taxonomy. This sequence forms a closed loop. Raw material taxonomy defines mechanical limits, and those limits dictate the selection of a formative or subtractive process. In mass production, the components for a single machine are often sourced from dozens of different specialized shops. To manage this, we rely on metrology, the science of measurement. It provides the strict dimensional control required to ensure decentralized parts are accurate. The goal of this system is interchangeability. Any part selected at random must assemble correctly with any other matching component. When these principles are applied correctly, we see disparate components sliding together to form a finalized functional engineering assembly. Manufacturing engineering is the mastery of this entire sequence, from classifying the raw material to verifying the final dimensional assembly.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.